Refraction occurs when the light travels between different media, and each one of those media has a different refractive index. But that to happen, the angle of the incident light should not be 90 degrees. Otherwise, if the incident light fell at a surface with 90 degrees, there will be no refraction. So this one is normal incident. We have different laws in refraction. Let's say we have two different media such as air and water. And here we have the normal, which means assuming the incident light is perpendicular to this surface, which means there will be no refraction. And we have incident light with angle of incident. Let's call it I. Since the angle of incident is not 90 degrees, that means the light will refract given the angle R. This is the first medium, which is the air, and this is the second medium, which is the water. And each one of those has a different refractive index, and refractive index determines whether the speed of the light will increase or decrease, which means in refraction, not just the direction of the light will change, but also the speed of the light. So the first law in refraction states that the incident light and the refracted light and the normal to the refracting surface all lie in the same plane. Law number 2, which we call it the Snell's law, states that the ratio of sine of the angle of incident light in the first medium to the sine of the angle of the refracted light in the second medium is equal to the ratio of refractive index of the second medium to that of the refractive index of the first medium. If we want to write it, the sine of the angle of the incident light to the sine of the angle of the refracted light, which is R, equal to the ratio of the refractive index of the second medium to refractive index of the first medium. This is the incident light, and this one is the refracted light. But how can we find the refractive index of anything? Refractive index is the ratio of the speed of the light in vacuum to the speed of the light in the medium. So let's say we want the refractive index of the water. The speed of the light in vacuum is about 3 by 10 to 8 meters per second. And the speed of the light in the water is about 2.2 by 10 to 8 meters per second. And the result will be about 1.33. That's the refractive index of the water. Each medium has a different refractive index and different speed of light. For example, glass has a refractive index 1.5. Of course, it depends on the type of the glass. Is it crystalline glass? Is it French glass? But most of them need 1.5, which means the speed of the light in the glass is about 2 by 10 to 8 meters per. If you notice, when the refractive index increases, the speed of light will decrease. So higher refractive index, slower light travels. Back to the Snell formula. Since the speed of the light changed by the change of the refractive index, that means those two will equal also the speed of light in the first medium to the speed of light in the second medium.
Each medium has a different refractive index and it's constant, which means always the refractive index in vacuum will be 1, in air almost 1, and that's mostly why we calculate the refractive index of air and the speed of light in air in normal problems as the vacuum. And each one of those media, water, glass, and one of those has a constant refractive index. Let's take the vacuum and the glass for example. That's the vacuum, and here is our glass. Here the refractive index is 1 and here almost 1.5, which means the glass denser than the vacuum, and vacuum is rarer than the glass. Here we have the normal, the perpendicular to the plane. When the light travels from rarer to denser medium, it will deviate or refract toward the normal. If we here complete this light of incident, it should be something like that. But since we have two different media, the vacuum and the glass, it will deviate to the direction of normal because vacuum is rarer than the glass. This angle, we will call it the angle of deviation. This is the angle of incident and this is the angle of refraction. So if the light travels from rarer medium to denser medium, such as from vacuum to glass, the angle of deviation D will equal the angle of incident minus the angle of refraction. On the other hand, if the light travels from denser to rarer medium, the light will deviate away from the normal. So in this case, the angle of deviation D will equal angle of incidence I minus angle of refraction. D equal I minus R. So from those we can derive some characteristic of refraction. This is the first one. When the light passes from rarer medium to denser medium, it deviates towards normal in the denser medium. Quite the opposite in the second. When the light passes from denser to rarer medium, it deviates away from the normal in rarer medium. The third one, in any refraction surface, there will be also some reflection. Let's say that's the plane and that's our normal perpendicular to the plane. Here we have the incident light and that's the refracted light. A very small part of the incident light will reflect too. So here we have refraction and very small part here will reflect, which means we have reflection here. Which means the intensity of the refracted light will be less than the incident light. Let's say the intensity here is 100%, 10% of it reflected and the residual 90 refracted. So the intensity of light here less than the intensity of light here. This phenomenon, in which a part of light from source undergoing reflection and the other part of light from the same source undergoing refraction at the same time surface, is called simultaneous refraction and reflection. In optical surface, we can put some coat here on the surface with suitable materials, so a part of light will refract and a small part of it will reflect, and this reflecting amount will depend on the amount of the coating on the surface. This is commercially called two-way mirror or semi-silvered mirror. Or even half silvered mirror. This technique, you can see it nowadays in the windows. So let's say that a window with semi-silvered mirror, here you are, and that's your friend. Your friend can see you, but you cannot see your friend. You will see your reflection on that window. So she can see you, but you cannot see her. The only thing you're going to see is your reflection. You can see this technique in the changing room. There is a method to test the two-way mirror. You can place your finger on the mirror. If there is a gap between your finger and the image in the mirror, that's a normal mirror, you are safe to change. If not, there is no space between your finger and the image in the mirror, be careful, that's a two-way mirror. Besides the simultaneous reflection and refraction, we have total internal reflection. Again, let's say we have the glass, and we have the air. Glass, of course, denser than the air, and the air is rarer than the glass. This is the normal. If we have incident light traveling from denser to rarer, as we said, it will deviate away from the normal. If that's your source of light and you change the position for here, for example, the incidence light coming from this side will refract like this. So you increase the angle of incidence, that immediately will increase the angle of refraction. Let's increase the angle more. This is the incident light. At some point, the refracted light will be at right angle. And here we're going to call it the critical angle. Let's increase that incident light angle even more. Here the angle of incidence in the denser medium is greater than the critical angle. The light this time will not refract but will totally reflect. So if the light traveling from denser to rarer and the angle of incidence in the denser medium is greater than the critical angle, the light will totally reflect. Since we're talking about angles, calculations and numbers, that's immediately the geometrical optics. If you noticed here in geometrical optics, when we talked about the light and when we draw the light, they are all a regular single line. We don't draw them as waves, neither particles, which is photons. Light again is waves and photons. They are not rays. But here in geometrical optics, we consider them as rays, which means a singular regular line, just to calculate an easier way with more accurate results. So light is not rays, but geometrical optics consider it as rays to be easier in formulation. The most common medium that depends on the basic of refraction is the spherical lens. And the word sphere immediately means ball. So let's say we have this first ball overlapping with the second ball, and here we have the third ball. Each one of those three is a sphere. If we cut this area like that, the result will be this lens, and if we cut this area like this, we will have this lens. As you can see, each one of those is part of the ball, is part of the sphere. So that means each one of those, number 1 and number 2, is part of the ball or part of the sphere. Lenses which bounded by two spherical surfaces, mostly made of transparent glass. And as you can see, we have two shapes. The first one bulks out at the center, which means it's thick from the center and becoming thinner at the two sides or the two edges. And this one we call it the convex lens. Quite the opposite, we have concave lens, which is thick from the side, thick from the edges, and thin in the center. Each one of those lenses have a center point. We call it the optical center. If we have a ray of light passing through this optical center, for both convex or concave lens, the light will go straight and doesn't deviate or doesn't refract. And this line that passing straight through the optical center without bending or refracting and remain as a straight line and perpendicular to its sides from the center, we call it the principal axis or optical axis. So what happened to the light that's not coming from the optical center? We will have something, we call it divergence. And we have two types. So we have light coming parallel to the optical axis in convex and concave lens. That's the direction of the light. As you can see here, the convex lens becomes thicker as we go to the center. Quite the opposite in concave, it becomes thicker when we go to the edges. So in convex lens, the light will deviate toward the optical axis. Quite the opposite in concave lens, the light will deviate away from the optical axis. Deviation toward the optical axis, we call it convergence. And that's why we also call the convex lens the convergent lenses. When the light deviate away from the optical axis, we call it divergence. So the concave lens, also we're going to call it the divergent lenses. If the light came from the left side, the rays will converge on the right side, and quite the opposite. If the light came from the right side, it will converge on the left side. This point on the optical axis, from right or from left, we call it focal point. So each lens has two focal points, on the right, on the left, and both are at equal distance from the optical center. If it's 1 centimeter here, that means it will be 1 centimeter here too. 1 meter, the other one will be 1 meter too, and so on. And this, of course, for both concave and convex lenses. Okay, perhaps you're wondering, in divergent lenses, how can we know where is the focal point if the light deviates away from the optical axis? So you can complete this one here like that, and immediately you will find the focal point in the concave lens. Here, let's say the distance between the focal point and the optical center is 1 meter. That means the second one also will be 1 meter too. This area of 1 meter, or whatever was the distance between the focal point and the optical center, we call it the focal length. So the focal length is the distance between the focal point and the optical center. This focal length depends on the refractive index of the lens, which is here. Mostly we have it from glass. The refractive index of the glass mostly is 1.5. Of course, we have different types of glass, but all of them, their refractive index something close to 1.5. It could be 148, for example, or it could be 1.52 in other type of glass. The focal length will decrease, which means become shorter. So number one, the focal length will depend on the refractive index, and number two, it will depend on something we call it the curvature. What do we mean by curvature? So let's say we have that sphere that we cut our lens from it, and this one is the second sphere. This is the center of the sphere, and those are the lengths that we cut from those spheres. The distance here from any point at the sphere and the center, we call it the radius. The radius here, let's say it's about 6 centimeters, for example, and here in the small sphere we have just 1 centimeter radius. The surface of the lens is an arc, and part from this circle or from this sphere, and this one here something like this. If you have noticed, the arc in circle number 1 or sphere number 1 is flatter than the arc in the sphere number 2, which means the arc of number 2 is steeper than the arc in number 1. It is steeper than the arc in number 1, which means when radius of curvature increase, the lens will become flat. When radius of curvature decrease, the lens will become steep. Here the lens will become almost flat. This one, the lens will become steep, deeper. This radius of curvature inversely proportional to the surface power, which means when the radius curvature of the sphere increase, the power of the lens will decrease. Quite the opposite, when the radius curvature decrease, the power of that lens will increase. That immediately means the flat lens has less power than steep lenses. The steep lenses more powerful than the flat lenses. So this area here is the curvature. the more bending of the surface, the more curved lens we have, which means immediately steeper lenses with higher power. Back to the curvature here. Flatter lenses will have long focal length and steeper lenses will have short focal length. So the focal length will decrease when we have high refractive index and more curved surface. So let's say that's the flat lens and that this steep lens. The focal length here will be longer than the focal length here in the steep lens. And as we agreed, steep lenses has higher power than the flat lenses, which means also this focal length will decrease as the power of the lens increase. Then the focal length also depends on the power of the lens. It will decrease or become shorter when that power of the lens increase. So all of them are relative to each other, and we can find equation from that. The surface power equal the refractive index minus 1 divided by the radius. For example, let's say we have a lens surface with 83.2 millimeter radius of curvature ground onto a type of glass with refractive index of 1.499. What the surface power of lens? We can compensate here. First thing we need to do is converting this millimeter into meter by dividing it by 1000. So the result will be 0.0832. That's the radius of curvature. Now it's by meter. And the refractive index here is 1.499 minus 1. The result here, we will divide it by this radius of curvature, and the result will be 6 diopter. So we measure the power by diopter. Back to our circle here. Let's draw a new one. Here is our convex lens. From here we can take the concave lens. So this one is the radius of curvature, and this one here is the lens diameter, and this is the arc of the lens. The diameter of the concave lens will be this one. So the distance between the center of this base of the lens to this point, the center of this arc, this distance or this height of the lens, we call it sagitta, or just shortly we can call it sag. This a Latin word means arrow. The height or the depth of the concave and convex lens, which is sag, we also call it the vertex depth. This is the sagitta area of these lenses, and this is the sagitta area or the sag for the concave lenses. Let's have a new circle. That's circle number 1 with flatter curvature, and that's circle number 2 with steeper curvature. Let's count half inch here, and the same for the smaller circle. Half inch here. This is the lens diameter here, and this is the lens diameter for the steep sphere. Both have the same height, which is about 0.5 inches. If you notice, the sagitta here is smaller than the sagitta here, although they both have the same height here, which is 0.5 inch. So as the radius of curvature becomes shorter or decrease, the sag will increase, and vice versa. The radius increase, the sag immediately will decrease. This means when the sagitta also increase, the power of that lens will increase either. And quite the opposite here, decreasing of sag will decrease the power of the lens. Why this sag is important? Well, sag provides the center location of the radius of curvature, thus allowing the fabricators to correctly position the radius on the optic, as well as establishing both the center and edge thickness of an optic. Let's say we have a glass here. You want to cut a glass for a client. This is the eye of the client. This area of the lens should be here directly in front of the eye of the client. By knowing the radius of curvature, which is this one, and the diameter of the lens, this one, the sag can be calculated by the following formula. Sag equal radius curvature minus square root radius curvature square minus diameter divided by 2 square. Our radius of curvature, this one here, and the diameter, which is here. So we have surface power refractive index and the curvature. Here we have sagita. When the surface power increase, the sag here will increase too. And when we have more curvature, which means steep lenses, we also will have increase in sag. And remember when we talked about the focal length, when the curvature increases, the focal length will decrease, which means immediately when this focal length decrease or become shorter, the surface power here also will increase. So inversely proportional. Short focal length will give us higher power. The other thing that affects the focal length is the refractive index. Higher refractive index, shorter focal length. So all of those are directly proportional except the focal length is inversely proportional. The lens power. Or also we can say lens diopter, because the lens power we measure it by diopter. So the unit of measurement of optical power of a lens is the diopter. And this diopter, which is the power of the lens, is the reciprocal of the focal length of the lens surface, which means this power equal to the inverted focal length. So if we have this convex lens, its focal length equal to the inverse of the power of this surface, if also the focal length equal 1 over the power of this lens, and we measure it by meter. Or if you want to do it by millimeter, we can say the power by diopter equal 1000 over the focal length, but this time by millimeter. Here by meter, here by millimeter. As you remember, we said we have two types of lenses, the convex lens or the convergent lenses, and the concave lens, which is the divergent lens. That's our axis, and this is the light collecting in the focal point. Since the light comes from this direction and collected in the other side here, that means they have positive focal length.
which making the convex lens positive. Immediately means they have positive power value. So here, let's say this one is 1 diopter. Since it's convex lens, we write it like that, positive 1. In the concave lens, the light will diverge like that. So you have to do the focal point like this. So the focal point at the same side of the incident light, which means they have negative focal length. And that's make the power value of this lens by minus. So the same 1 diopter, but here by concave lens it will be minus 1. So in the power of the lens you have to write those signs to determine is it concave or convex lens. We also can measure the curvature of the lens, and we measure it also in diopters as the reciprocal of the radius of the lens in meters, which means the curvature of the lens equal 1 over radius of curvature, and we will measure it also by diopter when the radius of curvature by meter. So this curvature equal to inverted radius of curvature of the sphere that we took this lens from it. So when this radius of curvature, for example, equal 1 over 5 meter, that immediately means the power of this curvature of this lens equal 5 diopter. You should never forget the sign. Since it's a convex lens, that means it's a positive 5 diopter. Let's take another example. Let's say we have a lens with minus 3.33 diopter. Can you measure the focal length of this lens? Well, F immediately will equal 1 over the power of the length, which minus 3.33. So the focal length of this lens is minus or 30 meter. And perhaps you're wondering how a distance with minus. That's because we have this focal length in the negative side of the lens. And since it's negative, that immediately means it's the concave lens. So the longer focal length, the lower power of this lens. The shorter focal length, the higher power of this lens. And the same with the curvature. Longer radius of curvature, lower power and less curve. Short radius, higher power and more curve. You can see the refraction by spherical lenses in everyday life all around you. For example, you can see the rainbow that formed by the water droplets, and also you can see it while you're drinking a cup of tea or even a glass of water. We use it to correct any refractive error in human eyes by normal glasses or spectacles and the contact lenses. Both depends on the refractive principles. We can use it in different systems such as microscope and telescope. And of course you can find it in the camera, even the camera of your phone. And most importantly, the refraction by the crystalline lens and the cornea in your eyes, so you can see clearly. The relaxed normal eye has an approximate optical power of 60 diopters, 40 by your cornea and the residual 20 by your crystalline lens.